But you got the answer, right?
Yeah.
Okay, cool. How about Harry or on? You guys got a question?
Yeah, I have a couple questions.
Okay, go for it.
Well, I have a question uh, on the homework, the Module 5 homework
Okay.
with
Which number?
well, it's with 1 and 3 and finding the theoretical yields.
1 and 3 and finding the theoretical yield. Okay, hang on a second here. Whoops. I'm trying to open up the homework. Module 5. Homework. And did you say number 3?
1 and 3 and finding the theoretical yield.
Okay, theoretical yield is just how much you can make based on what you started with. Now, let's see. In this case, we're starting with 10 grams of iron. Oh, we're looking at the very last problem, right? If 10 grams is reacted with 10 grams.
Yeah.
Okay, so what is the theoretical yield of iron 3 chloride? This is the way I do it. First, we need a balanced reaction. So iron metal with chlorine gas makes iron 3 chloride. And this is going to be a solid because it's an ionic compound. 1 iron, 2 chlorines, 3 chlorines. So I'm going to put a 3 here and a 2 here. And then because I put a 2 here, I'm going to put a 2 here. So this would be the balanced reaction. Are you with me?
Yeah.
Okay. So if we start off with 10 grams of iron, what I'm going to do here is I'm going to calculate the grams of iron 3 chloride that we could make from this, okay? So I'm going to convert the grams into moles. I'm going to double check this smaller mass. I don't trust my memory. Yep, that's good. And then here, there are 2 mole of iron 3 chloride per 2 mole of iron. And then the molar mass of iron 3 chloride is going to be 55.85 plus 3 times 35.45, which puts us roughly at about 110 plus, or 105 plus 55, or 160-ish. Now let me do the work and make sure that it comes out close to that. 55.85 plus 3 times 35.45. 162. Okay, so when we do the work, we can see that this goes into this about 3 times. 2 divided by 2 is 1. 3 times 10 is 30. So we should get about 30 grams. And I'm going to now check. And I get 29.0 grams of iron 3 chloride. Now I'm also going to start off with 10 grams of chlorine. This is the molar mass of chlorine. Here I'm going to use the balanced reaction. And then here I'm going to use the molar mass of iron 3 chloride, which I've already figured out is 162.2 grams. And when I do the work here, this goes into this 2 times plus a little left over. 2 times 2 is 4. 4 divided by 3 is like 1.3. 1.3 times 10 is going to be somewhere around 13. But maybe the answer is more like 15 because this goes into that more than 2 times. So it's going to be around 15-ish grams, and let's figure out what we actually get. 10 times 2 times 1, 62.2, divided by 70.90, and divided by 3. And we get 15.3 grams of iron 3 chloride. So what do we do with these two numbers? And the answer is, if I could make 29 grams of this, starting with 10 grams of this, and if I can make 15 grams starting with 10 grams of this, how much am I going to make? Well, let's make sense of this, okay? Let's say that we're making bologna sandwiches and we're really poor. So that means that we use 2 slices of bread and 1 slice of bologna, and that's it. No 2 slices of bologna, no 3 slices of bologna, 1 slice of bologna, 2 slices of bread. So do you understand the premise here?
Yeah.
Okay, great. Now, what if I have 10 slices of bologna? How many sandwiches can I make? Given that I have all the bread in the world.
Oh, you can make 10 sandwiches.
Great. Now, let's say that I have 10 slices of bread. Notice the 10 and 10?
Right?
Now, if I have 10 slices of bread, how many sandwiches could we make? Given that I have all the bologna in the world.
So only make 5 sandwiches.
Right, because you have 2 slices of bread per 1 sandwich. Now imagine that you had 10 slices of bread and 10 slices of bologna. How many sandwiches could you make?
You could make only 5 sandwiches.
5, because you run out of bread.
Right.
So you could make 5 sandwiches from 10 slices. You could make 10 sandwiches from, let me restate that because I didn't say 10 slices of what. You could make 5 sandwiches from 10 slices of bread. You could make 10 sandwiches from 10 slices of bologna. So which do you make, 5 or 10? The smaller of the two, correct?
Right.
So guess what we do here? How much are we going to make?
15.3 grams.
The smaller of the two. So this is how much you make because this is limiting. And what do we know about the other material?
Excess.
Excess. And we could actually do this way. 10 Don't ask me why you pronounce that baloney. I have no idea. Do you understand the conversion here?
Yeah.
And I'm not using the word slices here. So here, how much are we going to make from 10 and 10? You're going to make 5 sandwiches. It's the lesser of the two.
I have to move the paper down a little bit. You can't see
I'm sorry.
It's fine.
Let me go to my share screen so that I can see what I'm doing here. Okay, there we go. Actually, what I need to do is, this is blown up too much. There, now we can see everything. Okay, so here, you can see that between 10 and 5, we're going to make 5. And that means that this is limiting. And this is excess, because we're going to have, if we only make 5 sandwiches, we'll have 5 slices left over, correct?
Right.
So when you do this, the smaller number tells you how much you're going to make, tells you what's limiting, and the other one's in excess.
Oh.
This is how I do it. Now, there is another way to do it, and I'm going to show it to you very quickly. So let's say we start off with 10 grams of iron. I'm going to multiply by 1 mole of iron per 55.85 grams of iron. Then I'm going to multiply by 3 mole of chlorine per 2 mole of iron. Then I'm going to multiply by 70.90 grams of chlorine per 1 mole of chlorine. Okay, so when I do this multiplication here, you can see that 55 goes into 70 one time with a little change left over. Let's say that that makes this not 3 but 4. So 4 over 2 is 2. 2 times 10 is 20. So we should get close to 20. Let's see what we get. And we get 19.0. So I'm going to write out the words. So if we begin with 10 grams of iron, you need 19.0 grams of chlorine. So do you understand what I've written there?
Yep.
Now, we have 10 grams of chlorine, so not all iron can react. Do you understand that?
Yeah.
We need 19, but we only have 10. That means you can't react all the iron. So you have excess iron. Are you with me there?
Yep.
And chlorine is limiting. So now what we have to do is take our 10 grams of chlorine, multiply by 1 mole of chlorine for 70.90 grams of chlorine, times 2 mole of iron 3 chloride and 3 mole of chlorine, and then times 162.2 grams of iron 3 chloride per 1 mole of iron 3 chloride. And we end up getting 15.3 grams of iron 3 chloride. So that's how much we're going to make. And this is excess, and this is limiting. Are you with me?
Yep.
So how is this different than this? And the answer is a little different. We did this calculation in both of them. Do you see that?
Yeah.
Here we did another calculation for both of them, but those calculations are a little bit different. As far as what turned out to be excess and what turned out to be limiting, we got the exact same answer. So which way is better? And the answer is whichever one is easier for you to understand and put together. Are you with me?
Yeah.
Okay, so that's the deal.
Oh.
Now you said that there was a number 3 that also had a limiting, correct?
No, it's the theoretical yield.
Oh, the theoretical yield is the amount that you make based on the limiting.
Oh.
So I'm going to go back to this problem here. That's the theoretical yield.
Oh.
Now, the reason it's called the theoretical yield is that when you actually do these reactions, you're doing them in a pot. And from that pot, you have everything mixed together. Leftovers, product, solvent, all sorts of things in this pot. And you have to separate the product from everything else. The likelihood that you're going to get all of the product that you made and lose none of it is about 0. You're going to lose product. It always happens. So your actual yield always ends up being less than your theoretical yield. So the theoretical is based on everything being perfect, you being perfect. You're able to separate everything out. Not only that, but the reaction went perfectly. That means every molecule, in this case, of iron, or excuse me, every molecule of chlorine reacts, every one of them. Now this is a gas. That means that none of those gas molecules somehow escaped the container and made its merry way out into the world. Are you with me here?
Yeah.
So the theoretical yield is always better than the actual yield. And the theoretical yield is based on how much of the limiting reactant you started with. So if we take a look at number 3, you're asked to start with 1 kilogram of iodine. Oh, you want to prepare 1 kilogram of iodine. Oh, I'm sorry. If you look at this one, what's the theoretical yield if you mix 15 grams? So 15 grams of this sodium that's called sodium iodate, with 125 mils of 0.85 molar sodium. This is sodium hydrogen sulfite is what that's called. You have to do one of two things. Calculate how much I2 you're going to make from each of those, or calculate how much of one you need of the other. What makes this one a little different is that we have 125 milliliters of 0.853 molar instead of the mass. So this one you have to use a little bit of a solution concentration calculations to get the amounts. So let me show you what I mean by that, okay? So for this one here, I'm going to start off with 125 mils of sodium hydrogen sulfite. And then I'm going to multiply by 1 liter of sodium hydrogen sulfite. Normally I write the word solution here, but here I'm going to go ahead and write the formula of the dissolved material. And maybe what I'll do is I'll put aqueous here so that we know it's a solution. And then we're going to multiply by 0.125 moles Now here, I'm not going to write aqueous. I'm just going to leave it as the formula. And then times 5 mole of sodium hydrogen sulfite per 4 mole. And actually, I'm going to do this per 1 mole of I2. And then iodine is 128 or something like that, I want to say. 126.9. So 253.8 grams of I2 per 1 mole of I2. So if we started off with 125 milliliters of 0.125 molar sodium hydrogen sulfite, that's supposed to be a 3. Let's see how much we would get here. So I'm going to estimate this will go into this 4 times. 5 will go into 125 25 times, right? No, 25. Yeah, 25 times. 25 divided by, now I'm getting lost. This is, 4. This will go into that 5 times. So we have 5 over 4 times 0.125. And so the answer is going to be around 0.14. Okay? So let's see what we get. 125 times 0.125 times 253.8 divided by 1,000 divided by 5. 0.793 grams of I2. Why am I so far off with my estimating here? Let me check my numbers again. 125 times 0.125 times 253.8 divided by 1,000 and divided by 5. Well, I'm doing the numbers right. So here, this is made. Now, if we start off with 15.0 grams of sodium iodate, so sodium iodate is 22.99 plus 126.90 plus 48. So 9, 8, carry the 1. 17, carry the 1. 5, 1. I did that right. Times 1 mole of I2 to 2 mole. And then times 253.8 grams of I2 to 1 mole of I2. That'll go into that almost 2 times. So the answer should be a little less than 15. So we get 12.0 grams of I2. So if these are your 2 answers, how much are you going to make?
0.793.
0.793. What's limiting?
The 0.793.
No, what's limiting?
The NaHSO3.
Great. And what's in excess?
The NaIO3.
Okay, so that's how we figure it out.
Oh.
Do you see how in this case we had to do this little extra thing because we started off with a solution?
Right. Okay. And then I just have one more question. Just
Sure.
in regards to the lab, with the lab notebook, I'm having trouble with figuring out how to do the mass percent.
Mass percent of
Like,
based on formula or based on experiment?
I guess based on the formula.
Okay, so let's say that we want the mass percent carbonate in Na2CO3 based on the formula. That's what we're going to do, okay? So that's going to be the mass of carbonate ion in the formula divided by the mass of Na2CO3, the whole formula, times 100%. And I'm just going to round off. This is 60 grams. This is 106 grams. I'll let you get the better numbers than this, all right?
Right.
And you can see that this is going to be a little bit better than half, right? Or 50%. So 56.6%. So that's based on the formula.
Oh, and then would it be similar to doing it the experiment?
For the experiment, so the mass percent carbonate in sodium carbonate based on the experiment would be the mass of carbonate from the experiment divided by the mass of sodium carbonate used in the experiment.
Oh, okay.
right? You don't want to use the mass based on the formula. You want to use the mass that you actually used.
Okay.
So this ends up being somewhere around 0.5 grams. And this probably ends up being around 0.3 grams.
Okay.
And this would end up being 60%. Now, do you know how to get this?
What to get? Is it? I think I do, but I don't remember. I guess not really. No. Is it just?
You use the net ionic reaction.
Oh.
You weigh the solid. So you get the grams of calcium carbonate, turn that into moles of calcium carbonate, turn that into moles of carbonate, and then turn that into grams of carbonate. So grams to moles to moles to grams. This is a question that Jackie had asked earlier about how do you get the moles of carbonate? I think it was Jackie.
Can I have a quick question about
Yeah.
this? Yeah. So we what's it? Let me check. So we convert from the mole of calcium carbonate to carbonate. Are we using the ratio in the iodic net reaction? One, right?
Whenever you go from moles of one thing to another thing in a chemical reaction, use the coefficients from the balanced reaction.
So do we use on the net ion or on the reaction?
Well, here,
I just want to make sure whether I do it right or not.
I'm going to rewrite this.
Yeah.
So we're going to go from grams of calcium carbonate to moles of calcium carbonate. And then we're going to go to moles of carbonate, right?
Yeah.
So here, if we're going from moles of this to moles of this, then we want this balanced reaction, the net reaction.
Yeah. Okay.
And so it's a 1-to-1 ratio.
Yeah. That's what I try to make sure that I do it right.
Yeah. Well, since we're focusing on the carbonate, we're going to use the net.
Okay.
Okay. All right. Anything else? Nothing else? Okay, time to do some problems. So here we go. This is a stoichiometry of reactions and solutions. What mass of sodium carbonate is required for a complete reaction with 50 mils of 0.125 molar HNO3? So one of the things that we have to understand here is that this is moles of nitric acid per 1 liter of solution. Whenever you see this uppercase M, it always means moles of the solute per exactly 1 liter of solution. Okay? So you can see that we want grams of sodium carbonate. And since we have this balanced reaction here, chances are we're going to start with moles of sodium carbonate to get grams of sodium carbonate. And since they give us HNO3, we'll probably get to here from moles of nitric acid. And from the moles of nitric acid, we're basically going to start with the concentration. And here I should say, how do I say this? For this moles of nitric acid, you can see that if we have liters of solution, we'll be able to get here, but we have 0.125, whoops, 50 milliliters of solution. So here's the pathway. We're going to take our 50 milliliters of solution, convert it to liters, then use this and convert it to moles, then use the balanced reaction to get moles of sodium carbonate, and then get grams of sodium carbonate. So here's how you would write this out. And this is the best way to do this. You'd write HNO3 solution. So we're telling people what the solution is. And then we're going to write down 0.125 moles. And here's where students usually make a mistake and they lose points on an exam. They leave it uppercase M. Don't leave it uppercase M. Write out the word moles. And write 1 liter on the bottom. And you can see that when I have this unit plus label, it cancels very well with the next unit and label. And this unit and label cancels with this unit and label. And then from the balanced reaction, we have 1 mole of sodium carbonate to 2 mole of HNO3. And then lastly, the molar mass of this is about 106. So this is everything I would expect to see in your solution. And the answer should have 3 zig figs. I'm going to get the actual molar mass of this stuff real quick. 22.99 times 2 plus 12.01 plus 48. And it's actually 105.99. So here I have 3 significant figures. This is exact. 3 significant figures. This is exact from a balanced reaction. And 5 zig figs. So we end up with 3 zig figs. 105 goes into 1,000 10 times. 10 goes into 55 times. 5 times 0.125 is like 0.6. 0.6 divided by 2 is 0.3. So let's see what we get. 50 times 0.125 times 105.99 divided by 1,000 divided by 2. And we get 0.331 grams of sodium carbonate. And this, of course, will be part of the answer. So any questions about how I came up with my map and how I got the answer? If you're good, give me a thumbs up. If not, give me a thumbs down and ask so I can help explain it. Okay, well, I'm going to move on then. And here you can see we have another problem. Right there. I'll give you a chance to read it. Okay, can everyone see that we want the grams of hydrazine? What mass? Now, how do we get to the mass of hydrogen? Probably from moles of hydrazine. Now, since they give us 0.146 molar sulfuric acid, I imagine we'll get to moles of hydrazine from moles of sulfuric acid. If you're good with what I've done so far and you understand it, give me a thumbs up. Okay. I kind of like working these from the back end rather than from the front end, but you can work them from the front end. So if we were to work this from the front end, so I'm going to give this up. Can you see here I have a concentration and I have a volume? So chances are I'm going to start with the volume. And I could write 250 mils of H2SO4 solution, but to save space, I'm going to leave the word solution off. I'm going to convert that into liters of sulfuric acid. And then with this, I can convert that into moles of sulfuric acid. And then since I know this is my end run, I'm going to turn that into moles of hydrazine, because you cannot go directly to grams from moles of sulfuric acid. And then we'll go to grams. So you can start here and get to the end, or you can get to the end and find out where to start. It doesn't matter. You'll get the same pathway. The thing that's trickier about starting at the front is you have these two numbers, and the question is, which one do you start with? Well, this one here is actually moles of sulfuric acid per 1 liter of sulfuric acid solution, which means it's a ratio. This is not a ratio. And usually when you have one number that's a ratio and another one that's not, start with the one that is not a ratio. So you have the pathway, you have the numbers up here. I want you to work out the solution. I'll get you the molar masses. So this is 32.02. And this is 98.09. So once you have the solution all written out, give me a thumbs up and then we'll see how you did. I feel like I should pause it, but we've been waiting too long, so I'm not going to pause it. Maybe what I'll do is I'll play some music. Music that'll help you to do this.
Grammarly does more than catch errors. With Grammarly, you can find really good,
Oh, you already got the answer apparently, so I won't play the theme music. So let's take a look at the solution as I would write it out. And I'm going to try to write it a little more neatly than I've been writing in the past. So we'd have 250 milliliters of sulfuric acid. And I'm going to go ahead and go the whole 9 yards and write the word solution here. .146 moles of sulfuric acid per 1 liter of sulfuric acid solution. Did everyone remember to write the word mole here instead of an uppercase M? And then we're going to write from the balanced reaction 1 mole of sulfuric acid on the bottom and 2 mole of hydrazine on top. And then finally,
I think,
oh, I forgot something here, didn't I?
yeah, I was going to mention you forgot to get rid of the milliliters.
But that's okay, because even though I didn't do this step here, I can do it now. So it doesn't matter if you do them in order, although it makes a lot more sense to do it in order. I can put this conversion here. I just need to make sure that the right thing's on the bottom compared to what's on top. So not as nice as I'd like it to be, but it'll work. So if we estimate the answer, 250 will go into 1,000 4 times. 4 will go into 32 8 times, is that right? And then 8 times 2 is 16. 16 times 1.45 is around, let's see, 21. 2.1, excuse me. So 2.1 is our answer. Let's see what we get. 250 times 0.146 times 2 times 32.02 divided by 1,000. 2.34 and here I almost put liters here, but this liters cancels with that. This moles cancels with that. This moles cancels with that. The only thing that didn't cancel was this, so I get grams of N2H4. I almost put liters of H2SO4 because that's what I ended up with here. And this is one of the reasons why you don't want to do things out of order. It may mess up what you think are your units for your answer. All right, so how does that look? This is what I would expect on an exam. We're good? Okay. Let's do another one then. Okay, here we go. Okay, for this one, the 0.125 molar oxalic acid is 0.125 moles of oxalic acid. And instead of writing out H2C2O4, I'm going to write OA for oxalic acid. And this is per 1 liter of oxalic acid solution. This number here is 0.546 moles of sodium hydroxide per 1 liter of sodium hydroxide solution. And then we also have 35.2 milliliters of sodium hydroxide solution. So this is what we're given for the beginning information along with the balanced reaction. I'm going to go ahead and solve this one from the beginning rather than from the end. This, I'm probably going to start with 35.2 milliliters of sodium hydroxide solution. And I'm probably going to turn that into liters of sodium hydroxide solution because I know the concentration is in moles per liter. And then I can turn that into moles of sodium hydroxide. And you can see that the end answer is what volume of oxalic acid. So I'm going to put liters of oxalic acid here. So I need to go from sodium hydroxide to oxalic acid, which means I'll probably go from moles of sodium hydroxide to moles of oxalic acid. And then from moles of oxalic acid, I can go to liters of oxalic acid. So I'm just going to make this a really long arrow. And there we go. So that's the pathway. Now, notice here I left this as liters of oxalic acid, and I did not bother converting this to milliliters of oxalic acid. Now, the reason I didn't do that is because the question didn't ask me for milliliters. So why would I do extra work when I don't have to? In addition, when I do that extra work, I might mess it up. So if you mess it up, you're going to hurt yourself for the correct answer. So don't do more than you really need to. And if they give you a choice for volume, go with the easier volume to get to. So now that I have this set up, I want you to go ahead and solve it. When you think you're done, give me the thumbs up. And this time I am going to pause the recording. So if I follow the pathway more carefully than I did last time, I'm going to write 1 liter of sodium hydroxide solution on top and 1,000 milliliters of sodium hydroxide solution on the bottom. And then I'm going to write, according to the balanced reaction, no, I'm sorry, according to the concentration, 0.546 moles of sodium hydroxide per 1 liter of sodium hydroxide solution. And then we're going to multiply by 2 mole of sodium hydroxide on the bottom and 1 mole of oxalic acid on top from the balanced reaction, 2 to 1. And then we're going to multiply by this concentration, but I have to flip it upside down. And the reason I flip it upside down is so that the moles of oxalic acid cancel. And then I'm going to cross this and this out, cross this and this out, cross this and this. Not doing it too fast because I want to make sure that I'm crossing out the correct things. And I will get liters of oxalic acid solution as my final answer. And when we do all the work here, you can see that we have 1,000 times 0.125 is 125. 125 times 2 is 250. 35 will go into 250. Let's see, 1, 2, 3, 4, 5, 6, 7 times. So we have 0.546 over 7, which is almost 0.7 over 7, which would be what? 0.1, right? So if 0.7 over 7 is 0.1, then the answer should be 0.08 or something like that. 35.2 times 0.546 divided by 1,000 divided by 2 and divided by 0.125. And I said 0.08. It's not. It's 0.0769. Okay, so that's how many liters of solution there would be. So how do you all do on the final answer? Did we do okay? Give me a thumbs up if you did. Excellent. You guys are getting it. So the next problem is a titration problem. Oh, before we move on, actually, I'm sorry. So everyone sees this problem up here. What volume of oxalic acid? I know a lot of people like this thing called Khan Academy. And in Khan Academy, what they'll do for a problem like this sometimes is they'll say C1V1 is equal to C2V2. And so here you want the volume of oxalic acid. So V2 would be C1V1 over C2. So C1 would be 0.546 molar. V1 would be 35.2 milliliters. And C2 would be 0.125 molar. And let's see what answer we get here. And we get 153.7 milliliters, or 154 milliliters. Now, if we compare that to the real answer, which is 0.0769 liters, or 76.9 milliliters, can you see that the answer we would get using the Khan Academy method is twice the answer that you should get? So you may have been taught this also for a problem like this, where you're given the concentration of each thing, you're given the milliliters of each thing, and you're told to do something like this. I guarantee you, if you do this on my test, you will get the problem wrong, and you'll get essentially no credit for setting it up this way. Now, why is the answer 2 times off? And the answer is, this method is only good when the ratios are the same, 1 to 1, 2 to 2, 3 to 3. When the ratios are different, like 1 to 2, this method does not work. So never use that method in my class. It's a method that they sometimes teach in high school because they're trying to get through so much material. You only meet for an hour a day, and you guys have like 7 different classes. But in a college class, this is unacceptable, and you would get 0 credit for it. Does everyone understand that? Give me a thumbs up if you understand it. Okay. This way, on the other hand, when you look at the solution, it's very easy to see what's going on. Here, you're just converting from milliliters to liters. Here, you're converting from liters to moles. Here, you're converting from moles of one thing to moles of another thing. Here, you're converting from moles of one thing to liters of another thing. It's very laid out. It's very easy to understand, as long as you understand that when you have this conversion here, you're converting from one thing to another. You're either converting from the bottom to the top or from the top to the bottom. So this is very nicely laid out. All right, so here's your next problem, people. Only this time, instead of me telling you how to do it, I'm going to let you do it. Now, this says titrations versus stoichiometry of reactions in solution, but it's really the same thing. So this is stuff we've already been doing. I want you to see if you can solve this, and I'm going to give you a little time so that you can map it out if you want to. You don't have to. You know what I expect for the solution, so I'm going to leave it to you. You give me the thumbs up when you're done, and then we'll finish off with this last problem. Oh, and I'm going to pause the recording. So now my preference is to start at the end. What volume of HCl in milliliters? So this is where I want to get to, milliliters of HCl solution. And since I have molarity here, I imagine that I'm going to have to convert that from liters of HCl solution. Thirdly, since this is molarity, I should be able to go from moles of HCl to liters of HCl solution, because this says 0.955 moles of HCl per 1 liter of HCl solution. Now, they also give me this 2.152 grams of sodium carbonate, so that makes me think that I'm going to get to moles of HCl from moles of sodium carbonate. And lastly here, to get to moles of sodium carbonate, I see they give me the mass, and I know that if I can figure out the molar mass of sodium carbonate, I can go from 2.152 grams of sodium carbonate to moles of sodium carbonate. So this is going to be my pathway. Any questions about the pathway? If you have a question, just unmute yourself and ask. Okay, so now let's write out the solution. 2.152 grams of sodium carbonate times, and I remember this is 105.99. And according to the balanced reaction, I have 2 moles of HCl to 1 mole of sodium carbonate. And of course, the sodium carbonate goes on the bottom. And then here, I'm going to use this concentration, but I'm going to use this concentration upside down, which is fine. And then lastly, to convert it into milliliters, I'm going to use the old 1,000 milliliters of HCl solution per 1 liter of HCl solution. So if everything is set up correctly, I should be able to cancel labels and units. So I'm going to do that carefully. Grams, sodium carbonate on top, grams on the bottom. Those cancel. Mole of sodium carbonate on the top, mole of sodium carbonate on the bottom, they cancel. Mole of HCl, mole of HCl, liters of HCl, liters of HCl, and I'll be left with milliliters of HCl solution as my answer. And to estimate, 0.955 is 1. 105.99 goes into 1,000 10 times. 10 times 2 is 20. 20 times 2.1 is 42. So the answer is around 40, 42, something like that. We'll plug this in here now. 2.152 times 2 times 1,000 divided by 105.99 divided by 0.955, and I get 42.5 milliliters of HCl solution. And this has 4 zig figs. This has 5. This is infinite. This is 3. This is infinite. So with a 4, a 5, and a 3, we go with 3 zig figs in our answer. And the answer is 42.5 milliliters of HCl solution. Now, I'm going to tell you what, folks, you're going to see at least one of these kinds of problems on your exam, which is not going to come up this week or anything, but you do have a quiz this week. Now, on the quizzes, it's hard for me to put something so complicated on the quiz as a multiple choice type of problem. So you won't have anything this complicated on the quiz, but you will have things like, oh, how many moles of this to how many moles of that, and stuff like that. Okay, do we have any questions? Would anyone like to ask a question? So I'm going to take that as a no. I hope you continue to find these problem-solving sessions helpful in your trials. And remember, if there's anything I've done here today that you don't quite understand, it's okay to take a look at the problem again in the video, pause it, or actually not pause it, see the solution, and then back it up to where you just see the problem. See if you can solve it without the solution in front of you. Some people think, well, I'm not going to learn anything because I already saw the way to solve it. That's not true. Just because you saw it doesn't mean you know how to do it. It's just like the first time you made that grilled cheese sandwich. You saw mom make that grilled cheese sandwich again and again and again. And it just comes out perfect every time. And so naturally you think when you do it, it's going to be perfect every time. But what happened the first time you tried to grill a cheese sandwich? You burned it. Watching doesn't make you perfect. Doing does it. So how many times did it take you to make the perfect grilled cheese sandwich? I don't know, but it wasn't the first time. So do you understand the analogy, everyone? Do you guys like grilled cheese sandwiches? I'm going to clear you all. Are we good on grilled cheese sandwiches? 2 out of 3 ain't bad. Okay. Thank you for listening. I look forward to seeing you here on Friday. Turn your mics off and say goodbye to everybody.
Bye, everyone.
Bye, everyone.
See you Friday.
Wait a minute. I do have one more question for you guys.
Oh,
I'm pandering to my audience here, but do you think I should, in future classes, make people attend these types of things? Do you think it would help them?
I'm not sure because like some people they have busy, so I don't think they can attend it every day.
They don't have what?
They busy, they have work or anything, so I don't think they can attend it every day.
Yeah, I'm not really too worried about that because if we did not have the pandemic,
Oh,
you'd have to come to class anyways.
yeah.
So the pandemic actually makes it easier for them to not come to class, which makes it easier for them to not learn the material.
Yeah, like say you drop on a piece of paper.
Yeah, I think when you're in class and you're listening and I'm giving you the opportunity to do stuff in class and ask questions in class, you're going to learn a lot more than if you do it at home. And I wouldn't say you're going to learn a lot more, but you'll learn it faster. I bet you that your skills
Yeah,
in
that's true.
this 1 hour that we spend together a lot faster than 2 hours on your own.
Yeah.
So I'm thinking about making students attend class next semester. All right, folks, thanks for listening. You guys have a good couple of days, and I hope to see you on Friday.
Yeah.
all right.
Bye,
See
guys.
you then.
Bye-bye.
Bye.